Control theory is a bridge from natural sciences to means of transforming the world around us. It is a powerful set of tools that are used to run the technical equipment in human economy. Yet many of these tools come into being not without troubles that can be related to gaps between the theory and practice. This talk is about a particular means of filling such a gap. Let's take a look at what the usual control engineering business is like. First of all control systems are generally subject to certification via theoretical proofs of performance, stability, convergence, and safety, and so on, along with extensive experimental and simulation studies. Unfortunately, the theoretical part of this certification is not always directly translatable into sound control algorithms. And in fact, many tools that are being sold under the label of control algorithms are actually meta-algorithms, like, for example, model predictive control, that actually entails a fairly complicated meta step of computing an optimal control action sequence under the given dynamical model of the system while optimizing a finite horizon of so-called stage coasts. Now, this is a meta step, and such a meta step may actually be subject to imperfection and non-exactness of the computed optimizers. It may have internal dynamics that may lead to delay, and in general, influence of this meta step may be crucial for the performance of the closed loop altogether. What we are talking about here is a discrepancy between the theoretical proofs and meta-algorithms and their implementation. And this discrepancy can be understood in terms of so-called computational uncertainty. But the bad news is computational uncertainty cannot in general be submerged into usual kinds of uncertainty such as system noise or actuator noise. Uncertainty of this kind may lead to troubles such as loss of stability, poor performance, slow convergence, and so on. In fact, battling computational uncertainty is totally usual among control engineers. Tuning algorithms is sometimes done to a degree that it no more corresponds to the underlying theoretical analysis. It may be introduction of some tuning factors, even cherry picking. Well, in the field of reinforcement learning, which is currently probably the hottest topic in optimal control, there was recently a publication devoted to the effects of implementation on the closed loop under a method of reinforcement learning called policy gradient. And authors reported that certain implementation details could drastically influence the closed loop. The source of computational uncertainty in control theory is that it heavily relies on classical mathematics that allows existence of objects that are sort of ideal and are not translatable into reality in general. This concerns, for example, exact solutions to optimization problems, existence of eigenvectors, exact matrix decomposition, or asymptotic convergence certificates. On the bright side, what we are witnessing now is that the issue is being slowly recognized by the practitioners of control engineering. Recently, for example, there was a suggestion by Tsiotrias and Mesbah about the so-called algorithmic control theory. They brought attention to the computational uncertainty in control, but did not suggest a concrete framework to tackle. In contrast, Gao, with collaborators, suggested to use so-called epsilon stability and also so-called epsilon Lyapunov functions, where epsilon could be regarded as computational uncertainty. Computable analysis, which we'll talk about in a moment, was suggested by Collins and collaborators as foundation for control theory under computational uncertainty. Other authors suggested to use formal verification tools for the issue. Let's talk about some concrete methods to tackle computational uncertainty and generally how to fill the gap between the theory and practice. And the first tool that we will review is computable analysis due to Klaus Weyrauch. In computable analysis, every computation must terminate. Computable analysis uses relatively heavy formalism of Turing machines and so-called representations, which may not be so usual for a control engineer. On the other hand, unfortunately, computations need to terminate, but not necessarily in computable time. This can be referred to a Turing machine working on an infinite tape. The fact that the Turing machine will output an answer somewhen is sufficient to accept the computation, even if we cannot know when exactly this answer will come. Another group of methods can be summarized in formal verification. Formal verification tools are numerous. Probably the most popular one is being Coq, and then there is also an interesting piece of software called Chimera and Chimera X in particular that can be used to aid formal correctness checks of hybrid systems. And there is also so-called satisfiability modular theory solvers that can help resolve logical formulas on real numbers. These are, in general, highly abstracted programming languages that are also called proof assistants. They can translate logical deduction into special kind of code. So basically, a proof assistant can understand a proof, and it may even help automate the proof. Not only that, you can even extract a working program code from such a formalized proof. The whole matter can be, as of now, classified as rather esoteric for control engineers. And there are relatively few specially trained practitioners in this field. On the other hand, the extracted programs are usually slow as of now. Our suggestion is constructive mathematics, originally due to Brouwer with his celebrated intuitionistic logic, where every object claimed to exist must be provided with a procedure of how to actually find this object. Bishop then elaborated this idea in his Foundations of Constructive Analysis. Here, every computation, like in computable analysis, must also terminate, but in a computable time. And draw an analogy with programming languages. If computable analysis would allow while loops, constructive analysis would only allow for loops. So we will always know when the computation terminates. And Bishop specifically pursued language natural to mathematicians. So we can say that unlike computable analysis, the formalism of constructive analysis is more usual for a control engineer. Looking a little bit deeper into detail reveals the so-called realizability interpretation due to Brouwer, Heiting, and Kolmogorov. That is an interpretation that draws certain connections between logical formulas and computation algorithms. So, for example, an existence formula like this must actually be an algorithm that computes such an object A along with a certificate that the logical formula phi of A holds. And this object, A, is also called a witness. Here is an example claiming that some quantity L and depends on time t converge asymptotically to zero should actually mean that there is a finitely computable increase in map omega from the naturals to the rationals with the following property. So basically, this is a translation of asymptotic convergence into a sound computational language. And we call this omega modulus of asymptotic convergence. So for example, the famous Lassalle's principle for stability is actually vague in constructive analysis because there is no convergence certificate. Constructive analysis is evidently a much weaker system than the classical one, and also computable one. Yet there is a number of remarkable results that cover such complex subjects as general relativity, quantum mechanics, stochastic processes, measure theory, probability, and so on and so forth. And recently, application fields have started attracting attention. I should mention here Professor Yasuhito Tanaka from Doshisha University, who has been applying constructive analysis to foundations of mathematical economics. We thought why not to apply it to our beloved field of control. Luckily, a number of results was achieved, including approximate optimal control, measurable selectors that are used in some results in stabilization, viability theory, generalized trajectory existence such as Filipov solutions. We also provided some results in general stabilization of nonlinear systems via non-smooth Lyapunov functions and showed that in general computational uncertainty could not be submerged into the usual kinds of uncertainty such as measurement, actuator, and system noise. We observed that computational uncertainty had great influence on the system performance. Also provided some results in system analysis, including trajectory existence, stability, and studied approximate eigenvectors in an example with a linear quadratic regulator. Again, degree of approximation had great influence on the system performance. We also did constructive analysis of a sliding mode controller in a sampled setting where the system dynamics are continuous and the controller is time discrete. And we observed, again, great influence of the sampling time on the closed loop performance, and provided for the first time explicit computation of the sampling time on the required stabilization properties. And all these results, in my opinion, do provide a certain degree of optimism and a feeling of usefulness of constructive analysis for control theory. Here I give a selection of papers, and on the right-hand side you see the QR code that links to the survey paper that this presentation is dedicated to. So concluding, I think this is a nice tool to fill the gap between theoretical certification of control systems and their implementations. It has a language that is natural to a control engineer. Just extra care has to be taken of witnesses for logical statements. It bears educational aspect. Difficult concepts are easier to grasp when a clear translation into computer programs is demonstrated. And it offers new insights via enabling computations that were earlier not provided or were of no interest. As I mentioned, for example, in the stabilization and sampled setting or in sliding mode control.